All right, now it started. All right, a couple of announcements, although I think most of you were already good, but this at least applies to your other classes as well. If you have a Zoom class, make sure you sign into Zoom using your cuw.edu. That way you won't get put in waiting rooms. Because I think there's been some issues with teachers either not adding students to a class, or I mean, once I start sharing the screen, it doesn't always become obvious to me if there's like a chat message or if there's somebody waiting to be, admitted into the class, because there's a waiting room if they can't identify you as a cuw.edu person. So heads up, might want to just log in with your cuw.edu with Zoom, and then you won't have that issue. Secondarily, I just issued the Belt Awards upgrade from orange to green in class. So if you are due one of those, send me a Slack message or something like that, and I'll arrange to award you your belt. If you don't know what I'm talking about, last year I implemented kind of like a karate belt type of situation for our programming classes. So if you would like to get a belt as well, I'll look at what classes you've had and give you the appropriate belt based on that. And by belt, I mean, it's like a wristband thing. And you should be wearing these 24/7, Clancy. Have you been doing that?
Yeah, even when I sleep and shower and poop, all of the above.
I'm recording already.
I wanted to go on record.
Uh,
Let it be known.
I proved it to the class here, but I have a tan line related to mine from golf. So I even wear it for golf. All the time. It should be on all the time. All right. So how did the homework go? Easy? Ish? Ish? All right. So let's go through the homework first. And just like last time, if you have questions from the online group, interrupt me, shout it out, whatever, because I might not see like a chat thing or something. Or if somebody puts something in chat, somebody else bring attention to it, let me know in case they didn't have a microphone or something like that. Okay. Oh, I put Dr. Rackett down here, didn't I? So let's go through the homework, and then we'll start doing some other things leading to our next homework assignment. Okay, so we had 3 exercises that we did for this homework, and these are from the book. One thing I would point out, I mean, I'm sure many of you have already found it. I mean, this is a pretty popular book for programming language stuff. So obviously you could find the answers to a lot of these exercises online. I would encourage you not to do that. You're only hurting yourself. But, I'm sure some of you have already found it. If you need it to get you pushed in the right direction, that's fine, but it's not going to help you on exams and stuff. So just a heads up. Okay, so first one, duple returns a list containing n copies of X. We kind of almost wrote that last class, didn't we? So let's write that real quick. So if I have my second element, whatever this is, and you have duple of 2. So duple of 2 is going to give me a list containing 2 elements of this. All right, but I am going to show you a cool power tool today, but we'll define duple to be a lambda that's going to take in, what variables did they use? N and X. So we're going to take in 2 parameters, N and X. And we'll, remember last time we were kind of talking about patterns, right? And we should have seen we should see these patterns pop up pretty often here, right? So if we say if equal N0, boil down to the empty list. Otherwise, cons X onto duple of minus N1 and X. So if I do duple, is it duple 2, 3, something like that? That gives me a list of 3 3s. If I put this guy inside of a list containing 2 3s, I'll get a list containing, so this is a syntax some of you asked me questions about. So what this is doing is it's saying, I'm going to use this symbol, -1, negative, to represent the 2 list of 3. So this is saying my answer is a list containing a 2 list of 3 and a 2 list of 3. This is a placeholder for that. I do think if you really, really hate that, is it the, it might be the intermediate student. Yeah, the intermediate student won't put the placeholders in there. I would still say use the advanced student because those placeholders will come in handy later on when our things get more and more complex. But in any case, if you saw that -1 thing, that's what they were doing. They were saying, here's a placeholder, kind of like a variable for representing something. Okay, so questions about duple. And this should be well, I know we wrote this basically last time, what do we call it, repeat or something like that. But the idea here is we see this pattern where we're using a number to count down. We're constructing a list. List must end in an empty list. Well, you have to have a list as the second parameter, the last parameter of construct. So I'm consing my value onto whatever duple returns with a countdown, and my value with making sure my recursive stop case is a list. Okay, next one is invert. Invert lists, where list is a list of 2 lists. Okay, so 2 lists is a list with 2 things in it, and it returns a list with each of those 2 lists reversed. All right, so this one's called invert. And inverts a lambda that's going to take in what they call it list. I just want to name it the same as they called it. Yep. Going to take in a list. And what it's going to do is it's going to go through that list. And that list is a collection of 2 lists, right? And it's going to take each 2 lists and flip the values around. Okay? Now, this is where we get into potential, well, to make your life easier, helper functions. You could certainly put everything inside here, but what I'm going to do is I'm going to write a little function here called flip list. And flip list is going to be a lambda that's going to take a list in as a parameter, and it's going to create a new list out of that 2 list. And actually, I'm going to call this guy a 2 list. So we kind of know what that guy's taking in as a parameter. We know that that's the kind of thing. All right, so what we'll go ahead and do is we'll create a list out of the catter of 2 list and the car of 2 list. That's what flip list will do. It'll create a new list whose contents will be the second element in our first list, well, second element of this list, followed by the first element of that list as a list. You could have also done this if I wanted to write this a second time. Call this guy flip list 2. We can say I'm going to cons the catter of 2 list onto the cons of the car of 2 list onto the empty list. that will also construct that list. Okay, so then what are we going to do is we're going to have our pattern. So we're going to say if. Now, we want to keep going as long as this guy is not the empty list. Okay, so in the book, we have a way, it shows you to ask if something's an empty list, and a couple people asked me as well. We can say if a list is null, right? So if null list. So if I'm done building my list, I'll boil down to the empty list. Same pattern as before. Otherwise, I'm going to cons the result of flip list on the car of list onto invert of the rest of my list. So invert, we'll do 2, 1. Uh, 4, 3, 6, 5. And we get our 1, 2, 3, 4, 5, 6. Okay, so now I'm going to show you a power tool. All right, so we're going to call this guy invert2. So we'll write it first and then I'll explain it. All right, so there's my invert2. So we have a new function I've introduced here called map. And what map does is it allows you to map a function across every element of a list. So I have a function called flip list that if I apply that to this list, this element of this list, it would give me 1, 2. If I applied it to this element of this list, it would give me 3, 4. This would give me 5, 6. So I'm saying I want to map this function over each individual element of this list. But this function needs to take only a single parameter. There's ways of accomplishing something a little bit more complex, but in terms of map for you right now, this will only work if your function, in this case, the one that flip list is, takes in one input. So for example, I can say I want to map lambda x times x5 across the list 1, 2, 3, 4, 5, and we get each of those values multiplied by 5. Remember, lambdas are unnamed functions. This function didn't have to have a name. I am mapping this function right here, the function that takes a single parameter and takes whatever that parameter is and multiplies it by 5. I'm mapping it across this list of elements. So if 1 were to be passed into this, I'd get a 5. If 2 were to be passed into this, I'd get a 10. So on and so forth. 5, 10, 15, 20, 25. Make sense? All right, so map is a pretty powerful tool. Now, one word of warning is don't try to make everything, every solution, a solution that involves map. It doesn't apply to everything. So don't necessarily look at this as like, oh, it's my new go-to move. It is a powerful move, but it's not always something you're going to use. It's going to have to be situational, okay? But map is it's called a fun function that allows you to do some cool things. All right, questions about invert? All right, next one. Down wraps parentheses around each top level element of our list. So this would be an example of one where, so for down, I can say, define down to be a lambda that takes in a list. And what's this guy going to do? He's going to map the function list across lists. So down, 1, 2, 3 will give me the list containing the list 1, the list 2, the list 3. All right, so there's an example where map makes life way easier, right? Okay, but if we weren't using map for that, because we want to kind of focus in, I'm going to call this guy down 2. We want to focus in on that pattern thing. So we'll say define down to be a lambda that takes a list, and we'll ask the question, if null list, boil down to the empty list, else will cons the list version of the car of LST onto down on the footer of LST. There's our list 1, 2, and 3. So same pattern here as we saw right here, We're doing different things in the else, but we're consing. Actually, where's the normal invert? Yeah, we're consing. Okay, so this is like our 1-2 punch for working through things like this. Okay, so what I'm gonna do, let me just look at these next ones. Okay, let's actually solve these, and then the homework will be this guy, because I think this will be a good one to look at. Okay, so one thing I'll kind of point out is, as we're going through these right now, a lot of these things might seem like, oh, these are like little puzzle things, like what does this have to do with programming languages? You'll see once we come back around that we use a lot of these little things, these kind of little skills that we're writing here. They'll come back in our programming languages. Pretty quickly, we start working with lambda calculus stuff in these examples. So it's getting you used to scheme, sure, but it's also having us work on things that are actually related to languages. Go ahead.
Can you touch on a bit more of like scheme at a higher level? Like, is it a programming language that creates other programs?
That's how we're using it. No, so Scheme is a language that's a superset of a language called Lisp, L-I-S-P, which was originally created for working with artificial intelligence stuff. So it is a simplified functional programming language that can be used to kind of solve general purpose problems. I see it used most often when you're trying to, I use it obviously for language construction, but I see it used most often in just the generalistic idea of when you're trying to show when you're trying to show or work with a fairly complex task, but you don't want the language to get in the way. Scheme or Lisp, or because at this point we've used things. I mean, everything we've done you can do in Lisp. They are small enough that they don't get in the way of what you're trying to learn or do. Because I think sometimes what happens, and this happens a lot in Python, is the language almost has too much horsepower, where you can end up doing like the whole thing in one line, and then you don't really know what you just did, and then it's also not modifiable. So that's probably as good of an explanation as I can give. I can't necessarily give you like, I mean, there are GUI libraries and Scheme where you could, create games and stuff like that. I mean, it's doable. I don't think it's overly common. Today, Lisp was used for some weird things because Lisp has been around a while. So just dealing with list-based things, Lisp has been a pretty popular type things. And even just functional languages in general have been around. It's like, the programming language for the Texas Instruments graphing calculators is a functional language. But just this idea of having those simple primitives like car and cooter, and that just being the basis of like your whole world, is kind of an interesting way for you to be able to focus on the problem you're trying to solve and without the language getting in the way. I guess I'll stop at that. Does that help-ish, maybe? Okay, so first of all, I don't know if you noticed on these first assignments, they all were single star. Single star means easy. All right. This next one, we're going to run into a 2-star. And then what's your homework is, yeah, so your homework will be all 2 stars. Those are 2 homework assignments from now. Oh, we don't have the first 3-star yet? Oh, this is merge sort. My worlds are colliding. There are 3-star ones. Okay, so let's look at a couple of these, and then I'll interject some interesting tools that might help you in other things as we go through them. If we have time after we do these, I'll go and do the other thing I was going to do, which was just kind of more practice with stuff, but applying helper functions. But it seems like the helper function wasn't really a problem. At least nobody screamed online or in person, so I won't beat a dead horse there, I guess. All right, so we're going to write a function called swapper, which is going to take in 2 symbols as well as an S list. So it returns a list the same as that S list, but with all occurrences of S1 replaced by S2 and all occurrences of S2 replaced by S1. Now we have to look at our examples here. So for swapper, if we take in A and D, and we take in A, B, C, D, this first A will be swapped with D, this last D will be swapped with A, so we get that. Similarly, if we take in a swapper AD, and then we have this function here, those guys get swapped, not a big deal. But now this guy right here, swapper X and Y, notice that we have a list inside this. So we need to go back to our definition of an S list. All right, because this guy is an S list. So notice here that this is a list containing X. That symbol got processed to turn it into the Y. This top level thing got processed to turn it into X. And this list within a list got processed to turn it into a Y. Reminding ourselves, we just go back, I have our definition of S list. Yeah, here's an S list. An S list is 0 or more S expressions, where an S expression is either just a symbol or it's another S list. Make sense? So again, we're back to our reading our grammars, and this grammar has 2 productions. So an S list can either be just a symbol or it can be another S list. or an S expression could be just a symbol or another S list, where an S list is a collection of 0 or more S expressions. Okay, so let's get down into this. So we're going to create a function called swapper. So define swapper to be a lambda that takes in an S1, an S2, and an S list. And it should replace all occurrences of S1 inside of this S list with S2, and all occurrences of S2 within this S list of S1. All right, so I'm going to pause this now. So everybody go ahead and let's take 5 minutes. Try to write this yourself. You're probably going to run into, some of you will probably run into a wall. That's okay. I just want you to process some of the problems first, and then we'll go through and solve this as a group. All right, so let's take a look at this. So as we're going through our swapper, we have kind of 3 different things we might be looking at. Well, really 4 different things. So last time we introduced cons, right? So when you have kind of a collection of multiple things that could happen, a con might make some sense. Or you can just nest if inside each other. It's not a big deal. I'm going to go ahead and do a con here. And the first thing that I might be looking at is I might be dealing with something where the thing I'm looking at, the car of the list. Well, actually, we can start off with our first pattern, our null. If we're looking at null of S list, then we should just go ahead and boil down to the empty list. Technically, we'd also just boil down to S list since it is already the empty list. All right, so that's the first condition. If I'm looking at the empty list, I'm done with my cons because we're definitely constructing a new list here, right? Same as before, this is our old pattern, but now we kind of have some extra questions to ask in the middle of what's happening during the construction. All right, so now the car of the list. If it's not empty, the list definitely has a car, right? So car of S list is a thing. The question is what kind of thing is this? What are my options? What kind of thing could the car of that list be? Go back here to my definition of S lists.
A symbol?
Okay, could be a symbol or
Another S list.
or another S list.
Okay.
2 different things it could possibly be. So I'm going to say here that if the car of this guy is a list. Now, you see these things that have question marks on the end of them? That's kind of a naming convention. These guys are called something called a predicate. I'm going to go ahead and throw that into our slides here. So predicates. These are functions that take a single parameter and return true or false. For example, null returns true when given the empty list. List returns true when given a value that is a list and false otherwise. So you can think of predicates as kind of like testers. We're testing whether something is null. We're testing whether something is a list. You might imagine there's also one called symbol that returns true when given something that is a symbol. So these are ways of us at, well, we have another one for number. Tell me if it is a number, okay? So that's what a predicate is. So whenever you see the book use the phrase predicate, they're talking about a function that takes a single parameter and returns true or false based on some logic, okay? So what I'm saying here is if this guy is a list, then I need to do what? I'm ultimately swapping S1 and S2 in S lists, correct? If it's a list, that means it's an S list. How do I swap symbols inside of an S list?
You would can something onto the cutter.
Okay. Well, here, let me just put, pause this for now for that one, right? If it's not a list, it must be a symbol, correct? So if I'm still here, then I know this guy must be a symbol. So now I'm going to ask if the car of my S list is, I think it's equal, like that, to S1. Then I'm going to cons S2 onto the swapper of S1, S2, coder of S list. So if I'm currently looking at an S1, the symbol S1, then I'm going to swap it with S2. So I'll cons an S2 onto calling swapper again on the same S1, S2 symbols that I'm swapping, and the rest of my S list. Make sense? So this guy says if I'm looking at an S1, swap it with S2. This guy says if I'm currently looking at an S2, swap it with an S1. If it's not a list and the car is not S1 and the car is not S2, then what do I want to do? Yeah, I don't do any swapping, so I will cons the car of my S list onto whatever swapper returns for S1, S2, and the coder of my S list. So let's focus on these three. I'm going to call them productions right now. So because they should start sort of looking like the levels of our grammars. This says if I'm currently looking at something that is S1 at the front of my list, cons on S2 instead, and then call swapper on the rest of the list. If I'm currently looking at something that is S2 at the front of my list, cons on S1 and calls onto whatever swapper returns for the rest of the list. Otherwise, I'm not looking at an S1, I'm not looking at an S2, I'm not looking at a list. So I'll just cons on whatever was already there onto whatever swapper returns for the rest. So I still need swapper to finish processing the rest of my list, right? To swap in the other places it runs into. But now, back up to this. If I'm dealing with a list, if I'm dealing with a list as my car, I need to swap all the elements inside of that S list. How do I do that? Well, I'm consing something. Ultimately, I'm going to take the car of my S list, which I know is currently a list. But how do I process that guy? I'll go ahead and I'll say I'm going to call this on a swapper S1, S2 of the coder of S list. Because this will swap S1 and S2 on the rest of the list, right? But how do I deal with this guy? If the car of S list is a list, which means he is a S list, how do I deal with him? Go ahead.
You have to call swapper on the car of S list.
Why the car of S list?
Well, you have to go through something.
Let me ask you this. Do I happen to have a tool available to me that knows how, don't get ahead of me. Do I happen to have a tool available to me that knows how to process an S list and swap two symbols? What's it called? Swapper. So can I just say swapper S1, S2 on that list? So I'm going to cons the result of calling swapper on the car of the list, which is a list, onto, I'm going to kick this down so it's all on the same screen, onto whatever swapper S1, S2 returns for the rest of my list. So if my list is null, return the empty list. That's my old pattern. That ends it, right? Otherwise, if I'm looking at a list, that must be, it's an S list. If the car of it's a list, it's an S list. So I'm going to go ahead and cons the result of calling swapper on that car onto the result of calling swapper on the rest of the S list. I have a tool that's perfectly capable of doing the swapping stuff. It's called swapper. Might as well call it. Make sense? Now, up to this point, I think we've only used single equal signs for comparing things. So that's for numeric comparisons. Now I'm comparing symbols. So we use EQ. Actually, let me just go ahead and give you the, I'll use another thing in case we get to the other thing I was going to use. Scheme equal EQ, EQV equal. I'm going to go, well, let's see if they do a decent job. No, could be, because we have 4 different kind of Boolean comparators. Single equal sign is numeric. EQ question mark is like the basic, almost like char comparisons, looking at whether 2 strings are the same, symbols, comparing symbols. Excuse me. Okay, so let's start with the EQ here. I think this gives me a pretty decent thing. So when you use EQ question mark, this guy returns true if V1 and V2 refer to the same object. So this is kind of like if you think back to Java, pointers. If they equal the same pointer, if they equal the same literal, that's the EQ question mark. So remember when we go through that exercise in 250, where let's see, did you guys have Java in 200 or you had Python in 200? You had Java in 200, the first class? Python in the first class, Java in the second class. So in Java, when we go through and we look at like that example of having strings being equal to each other, like hello, you know, string S is equal to hello, string S2 is equal to hello, and S equals S2. But then we say string S3 equals new string hello, and they're not equal to each other because they hold different memory addresses. So when you have a symbol, a literal value, so you'll see the book calls these guys literals very often. You've heard me refer to it as something as a literal before. Like 5 is the integer literal for the number 5. Hello, double quote, is the string literal called hello. And in Java, the first time you use that in your program, it gets, a memory location gets created in Java literal space to hold that string. The next time you use that literal, it just links it to that same space. It doesn't create a new space. That's why the pointers match that same one literal space. Okay, so EQ question mark here is saying, are these guys the same object? Do they point to the same place? Okay. EQV, equivalent, 2 values are equivalent if and only if they are equal Oh, this is for the data type stuff. So for us, since I'm not using data types in our thing, you can say EQV and EQ are the same. Some data types might have a differentiating thing for, you might write like a special Boolean version for how to check to see if two objects are equivalent to each other. You know, like if we want to think about that in Java, we might say, well, a person is equivalent to another person if their age happens to be the same, as opposed to them being the same memory address, something like that. So otherwise, we could just treat them as being the same. And for us, since we're not creating objects in Scheme, it will be the same. So we really will never have a reason to use EQV in here. We can just use EQ. We can use these guys interchangeably. Equal, two values are equal if and only if they are equivalent unless otherwise specified. Data types with further specialization include strings, byte strings, pairs, mutable pairs, vectors, boxes. So this is giving us things that already have that new level of definition. Let's see. The best example of pairs we might run into, strings we might run into depending on what we make our language look like. So this is saying if you're going to compare strings to each other, you cannot compare them using EQV or EQ. You have to use equal to compare strings. I like to think of equals kind of like you're looking at bone structure. You know, it's not pointers, it's actually looking at content. But EQV could be looking at content too. Do they give some examples of built-in things? Oh, it says character data types, which are different than symbols in Scheme, would operate differently for EQV. I don't think we have to worry about that. So basically for us, the shorthand would be, if we're going to be comparing strings, we have to use equal. I don't know if that's going to be something we're going to run into. It's going to depend on the class decision when we get to what's the syntax for a language look like. Otherwise, if we're not using numbers, we can use EQ. If we're comparing numbers, you can use equal, the equal sign. Okay, so these are just ways of testing whether things are equal to other things. Generally speaking, I actually, if you just never want to be wrong, you could just use equal forever. Equal is like overkill, but equal on two numbers will boil down to true if they are the same number. So it's not encouraged, but it's technically it'll work. All right, so going through this, if we're looking at the empty list, we have our normal pattern. We're finishing a cons. Finish with the empty string. If we're looking at a list, what do we do? Well, we cons the result of swapper on that list onto the cons of swapper for the rest of our S list. Otherwise, we must be looking at a symbol because it's not the empty list and it's not a list. So it must be a symbol. And how do we handle symbols? Well, if the symbol matches S1, we swap it with S2. If it equals S2, we swap it with S1. If it doesn't equal either of those, we just cons the value as is on, no swapping, onto the swapper of everything else. Make sense? All right, so let's run this guy. So we'll do one of our simple cases, AD, then ABCD. Swapper AD, ABCD. Remind me, why did I put these little single quotes before these things? Yeah, so this indicates, well, this indicates it's not a variable, which probably is related to a function in our world right now. And this one says, don't treat this guy as the name of a function. So there's our swap DBCA. Then let's go down to our more complex one. Swapper XY. And this is on the list containing the list X. a Y, the list. Oh, it had an X again. I think that's it. So there's, it swapped the X and it swapped the X. Oh, and it swapped this Y with the X. All right. So common issue people run into on that particular one, and this is where you have to ask yourself, make sure you refer back to the grammar, is we see this thing's called an S list. The book has already introduced the grammar for S lists. But if you only look at these first two examples, you don't break based on that. Well, actually, the first example is the easy one, right? It just says, oh, it's just like a list of symbols as opposed to an S list. And a list of symbols is just a list containing several symbols. An S list is a list containing symbols as well as other S lists. So this guy we probably would have broken on, but since it didn't have, we could have, the way we could have written it originally is just saying, oh, we're just going to look at the car and see if it's equivalent. So we just would have seen that the empty list is not equal to an A or a D and just kept it. So we also could have probably passed this guy right here with just our normal version of this, not really considering we might need to call swapper recursively for the car. This is where it becomes more complex because we have S lists inside of our S list. So this S list contains an S list, a symbol, an S list, which contains a symbol, which contains an S list. Well, a symbol followed by an S list, which contains a symbol. More complex. All right, so questions about this one with swapper? We're at it 225 or 35? 25, okay. Next one, list set. Takes in a list, an N, and an X. And this returns a list just like list, except that the nth element using zero-based indexing, which we're used to, is actually X. All right, so we're going to take in a list, and what we're going to return is the exact same thing as that list currently is, except bucket N will be equal to X. Make sense? So if I have A, B, C, D, and I say I want bucket 2 to be equal to list 1, 2, we have AB for bucket 0 and bucket 1, but now bucket 2 is 1, 2. Okay, so we're going to need to look at our pattern of counting down along with our consing pattern, right? So we're going to process our list. So we're going to have that whole thing of processing the list, but we're going to need to do our counting down type thing to keep track of where we are in the list. What bucket are we currently at in the list? Does that make sense? Okay, so let's just start walking through this, but we'll try to do it somewhat interactively. So we'll define, what did we call it? List set. Taken to be a lambda that takes in a list as well as a N and an X. All right, so that's what list set is going to do. Now, I'm going to create a helper function to help me do this. They've told me to write list set so that these are the parameters it takes. So I'll just close that off for now first. Thank you. All right, so now we're going to say we're going to define a list set. I'll just call this helper because it's a helper function for this. And this guy is going to take in a, actually, will we need, we won't need to do the helper for this. Because we already have our counter. This is a bucket 2. We're going to count that guy down towards 0, right? All right, so we're going to go ahead and we're going to say if our list, we'll do this as a cond. So null list is going to boil down to the empty list. That means we've finished processing this guy. Now we could make the argument here that the n they give us is a always legal. If we make the argument, like for instance, they might say replace bucket n with x. Well, what if they give us an n of 4 million and there's only 3 elements in our list? We technically would never get to the element we should be swapping, right? So if we pretended like they always gave us a legal n, we actually would not need this first line. Because we would, and you'll see why in a second, but we would always unnaturally end the function. Except in the occurrence when it's, no, we would always end unnaturally. But we'll throw it in there. It's not going to hurt anything. So if I'm done, since I am building a list, right? I'm going to be doing some conses. So since I'm building a list, if I'm done, we'll just return the empty list. Otherwise, we're going to ask the question, if equal n0, as I've counted down, if I'm at a 0, that means it's time to do my swap. I want to cons an x. Instead of what currently is the car of the list, I want to cons an x onto what? This is where the trick is on this one. And here, actually, what I'll do is I'll just put some dots in there for a second. We'll come back to it. We'll have our else now. So if n is not equal to 0, then what I'll do is I'll go ahead and I'll say I'm going to cons the car of list onto list set of the cooter of list along with minus n1 and my x. If you like it spelled out a little bit more, you can always kick it down the line. So if I'm not in an n equals 0, meaning I haven't gotten to the bucket that I should be swapping, I'm going to cons whatever's currently in the front of the list onto whatever list set returns on the rest of my list, decrementing n by 1, and making sure I pass along the thing I'm going to swap out. So the question is, when I do get to my swappy point here, I'm going to cons my x. Instead of the car of the list, I'm consing on the x. But what am I consing it onto? Go ahead. Element after the one we're replacing. Well, let's go back here and look at our example here. So for list set, if I am replacing bucket 2 here with a C with my 1, 2. So I just got down to an n is 0. So I'm looking at this guy. So rather than consing on the car, I'm going to cons on my list 1, 2. And what am I consing it onto? What's left? It's a list D, right? If I look at, does this next one come earlier? 3, 2, no, it does the end. That's fine. So it's not the element after it, it's the rest of the list, right? The question is our pattern up to this point has always been called list set. So if I go ahead and I say, okay, well, I'll cons x onto whatever's returned by list set of the cooter of my list, passing it, I mean, I can do my whole minus n1 thing again if I want. I just need to make sure that n never becomes 0 again, right? And then I'll pass it x just because that's a parameter that's required by list set. But effectively, by me going, if I'm at 0 right now and I just went to -1, I know I'm never going to hit this again, right? It'll go -1, -2, -3, blah, blah, blah. Okay? So I'll go ahead and call this on this one. So this is ABCD212. All right, so we see our AB bucket 2 got replaced. But I'm saying that we actually could have written this more easily. This should be something else right now. To get me the same result. Did I have to call list? Oh, go ahead. Did I have to call list set again? Did I have to recursively call list set again? Go ahead. Well, what does append do? We're not guaranteed that X is a list. It's okay. You're just move away from the append thing, and you're still on the right track, I think. What's the second parameter of a cons? Well, do I have a list other than what can be returned by list set? The cutter. So this is actually my stop case, right? I'm not making any more recursive calls. So I'll cons X onto the rest of my list. I can do that because I don't need to process anymore in that list. I don't need to do any more. I don't need to do any more list setting. I already got to my N is 0. I found my place where I'm swapping out. So I'm just going to cons this onto the rest of the whole list, unchanged. And that's why I said earlier, if we assumed that N was always a legal bucket, we don't even need this part of the pattern. Like we won't hit that part of the pattern in this one, because we actually died out right here. When we finally did our swap and just consed it onto the footer of the list. We never hit the production that says, is the list null? That make sense? All right, count occurrences. You see that one we just did, that was a 2-star. Does that feel harder? And 3 stars, like defenders of God. Think archangel level stuff. Half the class drops today. Okay, count occurrences, we'll do this last one. It's gonna take a symbol as well as an S list. What's an S list? An S list is a list containing 0 or more S expressions, where an S expression is a symbol or an S list, right? Okay, so want to remember that that's a somewhat complicated, a more complicated grammar than just a list of symbols. Okay, we have some depth to it. So count occurrences, we want to return the number of times the symbol S occurs in this S list. So we'll define count. Do I even know how to spell occurrences? Too many R's. Occurrences like that? Geez, that's a word you shouldn't write. And then S list. Oh, sorry. That guy is a lambda. It takes a symbol and an S list, and it should return the number of times S occurs in that S list. All right, so we'll do our cond here. and we can say if we are done with our S list, done processing it, what are we going to return? Now, this is a new pattern for us, right? Because this time we're counting. We're not building a list, we're counting. So if I have nothing to look at, I'm looking at the empty list. How many occurrences of S are in the empty list? Okay, so I have a giant bucket here, and the bucket is empty. And I ask you how many quarters are in this empty bucket. What's your answer?
0.
Good. Even Noah got it. That meant to be offensive.
Thank
you. That's recorded. All right, so if I'm looking at the empty list, if S list is null, there are 0 occurrences of S in there. Why am I going to return 0 here? Because count occurrences job is to return the number of times I find this dude in this dude. Make sense? So if I'm looking at the empty list, I found 0 of them. If I'm not looking at the empty list, now I have to look at the car. Now, the car could be a list or it's a symbol, right? So if it's a list, S list, sorry, a list of the car of S list, if that guy is a list, then what do I want to do? If the first element of my S list is another S list, and my job of count occurrences is to return the total number of times S occurs inside of my big S list, what would I do? Okay, so here am I. Well, close to what we did in the first one. So you want me to call count occurrences on the car of S list, okay? And what else? Who? Kadur. Why? Oh, the Kuder. Why are you trying to pronounce the Kuder? See, you only do the weird pronunciations when you have like the extra A's and the extra D's. Like Cadder, or the Kadadur, or the Kadatter. Oh, the Kadatter is a fun one. So you're saying CDR, Kuder. Okay, Kuder. So you're going to take, what do you want to do? Count occurrences on the Kuder of S list? Like that? Yeah. Okay, and what am I going to do with those two dudes? Right now, they're just sitting out there. What does count occurrences do? What's the job of that function? Well, I mean, yeah, so keep it even more simple than that. Count occurrences counts the number of times that a symbol, in this case, my symbol S, I need to make sure I call that guy. How many times this symbol occurs in this S list? Count occurrences returns the number of times this symbol occurs in this S list. If the job of count occurrences is to return the number of times S occurs in this entire S list, and I'm calling count occurrences twice here, what do I need to do with those two returned values of count occurrences? Add them together. If my goal is for count occurrences is to return the total number of times that dude appears in this S list, and I found a situation where I have an extra S list, I need to add together whatever count occurrences returned for that first S list with whatever count occurrences returns for the rest of my S list. Okay, if it's not a list, I need to say, is the car of S list equal to S? If it's equal to it, what am I going to do? I'm going to add 1 to whatever count occurrences returns for the cooter of my S list. Else, I'll just call count occurrences on the rest of it. I could say add 0 to count occurrences and the rest of it, but I don't need to. I didn't find a match, so I'll just go ahead and call count occurrences on what's left. All right, I'll put this code up on Slack for you to review. I'm 103% sure it works. So for next class, actually, we're going to do homework 3 from the slides. Okay, but I'll give you all this code as a starting point. So homework 3 has all 3 2-stars. Okay, so if you haven't already started, you won't be done by Thursday. All right, I will see, because we're done, right? Okay, I will see everybody on Thursday.
Professor Lippman,
Yep.
super quick question. Can I share my screen with you so you can see this?
Yeah, give me a second.